Have you ever been in a situation, maybe at work or, even at home, where things just keep breaking? Like machines constantly glitching out,
Hmm.
electronic systems failing unexpectedly, maybe even light bulbs burning out way too fast, and you just can't find a clear cause.
Yeah, it's like this invisible gremlin in the works. It's a frustrating mystery for so many places, right? Leads to endless troubleshooting, wasted money, wasted time.
Absolutely. And well, today we're going to try and unravel that mystery, this deep dive. We're going to pull back the curtain on this hidden world of electrical forces. They're called harmonics.
Right.
And we're going way beyond just simple power quality issues here. We want to uncover how these, well, often overlooked electrical disturbances, from power lines, the ground, neutral wires, even inside the machines themselves, how they're silently messing with reliability and efficiency,
Mm.
especially in things like electric motors.
Yeah, and other critical systems too.
Exactly. So we spent some time digging into a specialized report all about how harmonics impact electric machine reliability, our mission, to pull out the key insights for you.
And hopefully by the end of this, you won't just know what harmonics are, but maybe more importantly, why they cause these widespread, kind of puzzling problems.
On what can actually be done about that.
Exactly. What steps you can take.
Okay, let's start unpacking this. When I hear harmonics, honestly, my mind jumps straight to power quality, what's coming in from the
Oh,
utility.
pretty standard, yeah.
But this report, it seems to be pushing us beyond just that. What exactly are these self-generated electric machine harmonics? And, why are they, plus the ground and neutral harmonics, becoming such a big overlooked issue now?
Yeah, that's a really crucial distinction. I mean, power harmonics are important. We talk about them a lot. But this research really highlights that the harmonics generated by the machine itself and the harmonic content lurking in grounds and neutrals, well, they're often missed. And the problems they cause, they seem to be popping up more and more frequently. We're talking about really specific, kind of baffling issues that, on the surface, don't seem to have an obvious explanation.
So what kind of specific problems are we talking about? What are the clues that point towards these non-power harmonics?
Well, you've got things like nuisance tripping of protective devices, those breakers that just seem to go for no reason.
Oh, yeah. Infuriating. Stops everything.
Exactly. And then we're seeing a rapidly increasing number of bearing defects. They look like electrical discharge damage, fluting, pitting, that kind of thing.
Okay, bearing failures, that's common enough, but...
Right. But here's the surprising part. This is happening even when a machine is running across the line. So directly connected to the grid without a variable frequency drive, a VFD.
Ah, so you can't just blame the VFD,
Yeah.
which is often the first suspect for bearing currents.
Precisely. That's what makes it so puzzling for a lot of people.
And I guess it doesn't just stop with the bearings, right? It sounds like it ripples outwards.
It absolutely does. You see failures in sensitive electronic systems, insulation starting to break down, power electronic components failing prematurely. It might even explain, like you said earlier, why you're changing light bulbs constantly.
Or why that big energy efficiency project didn't quite deliver the savings you expected.
Exactly. It's that puzzling lack of savings. It's often a much broader electrical system problem than just the quality of the power coming into the facility.
Okay, so let's maybe circle back to power harmonics for a second, the usual suspects. There's tons of info out there, I know, but what's really critical from this report's angle, how do those power harmonics actually link up with these other problems in the neutral, the ground, even inside the motor?
Yeah, that's the key connection people often miss. They think of power harmonics as, existing in their own little box. But the report really emphasizes that high-power harmonic issues, they don't stay contained. They will impact those other harmonic considerations, neutral, ground.
And make things worse inside the motor, too.
Yes, they can exacerbate the motor's own stator slot and rotor harmonics. It's like a chain reaction. Everything's connected electrically.
And what about the marketing aspect? I mean, you see ads for low harmonic drives, clean power systems all the time. The report suggests this can sometimes blind us.
It's a bit of a paradox, isn't it? You might invest heavily in, say, a low harmonic VFD, thinking, great, problem solved. But that very marketing focus can make you overlook the bigger picture.
How so?
Well, you could still be, as the report puts it, stuck with unusual system problems that may or may not appear to have any relationship to the device you installed, because you only addressed one piece of the puzzle.
Like fixing one leaky pipe, but ignoring the foundation crack.
Guess it's a good analogy, yeah.
Yeah.
You fix the obvious symptom maybe, but not the underlying systemic issue.
Okay. So sticking with power harmonics, the report details 4 main types. We know the common third harmonic, right? Often from single-phase loads like computers and lighting.
Yes, and that third harmonic is particularly nasty because in a 3-phase system, those third harmonic currents from each phase actually add up in the neutral wire instead of canceling out.
Leading to overloaded overheating neutrals.
Exactly. It's a major cause of neutral conductor failures. Then you've got the 5th harmonic. The report describes it as a counter-rotating harmonic.
Counter-rotating, so it pushes backwards against the motor's spin.
Basically, yes. It creates a magnetic field rotating in the opposite direction to the main field. It actively tries to slow the motor down, causes extra heating, vibration. It's just negative torque.
Wow. Literally fighting the machine. That sounds incredibly inefficient.
It is. And then number 3 is the 7th harmonic. This one's described as pro-rotating. So it rotates in the same direction as the motor's main field.
So that one helps then.
Well, it does add a bit of torque in the right direction, but it's still a higher frequency, so it contributes to additional heating and stress inside the motor, particularly in the rotor windings. It's not good harmonic content.
Okay. And then the 4th type mentioned are the overlooked even harmonics, the 2nd, 4th, 6th. I feel like I was taught these don't really exist in balanced 3-phase systems.
That's a common simplification, but this report is clear. They very much do exist. Maybe at lower levels, typically in, modern, well-balanced power systems, but they're definitely there.
And what causes them, if not just standard loads?
Well, they can come from standard nonlinear loads too, but they're often associated with asymmetry in the waveform. Things like electrical faults, even minor ones, loose connections creating intermittent contact, arcing, partial discharge, corona effects.
So system imperfections generate them.
Yes. Also, significant voltage or current unbalances between the phases, and importantly, magnetic core saturation, like when a motor or transformer is pushed beyond its design limits, overloaded. So yeah, they're more common than people think.
Okay, this brings us to something really interesting almost. Deceptive, the report suggests. Power factor. What's this difference between true power factor and apparent power factor? Why is it so critical?
Oh, it's a huge difference, and it explains a lot of mysteries. Most people, when they measure or talk about power factor, are looking at what's called apparent power factor, or PFA.
Right.
That calculation basically only uses the voltage and current at the fundamental line frequency, usually 50 or 60 hertz. The report gives an example where the PFA was, a pretty respectable 0.92.
Sounds okay on paper. No major red flags there.
Exactly. But then you look at true power factor, or PFT. The crucial difference is that PFT includes adding all of the current values for each harmonic into that calculation.
So it accounts for all the current flowing, not just the useful fundamental frequency current.
Precisely. And in that same example, when they calculated the true power factor, including all those harmonic currents, it dropped dramatically, down to 0.38.
Wow, from 0.92 down to 0.38. That's massive.
It is. And that huge difference reveals all this additional current in the circuit that the apparent power factor completely misses. This extra current isn't doing useful work. It's just circulating, causing heat and problems.
Like what kind of problems?
Serious ones. The report mentions slow starting of electric machines because the motor isn't getting the clean power it needs. Also, damage to electronic systems sensitive to these distorted currents, and significant extra loading of the transformer, potentially overheating it.
So what's the fix then, if you discover your PFT is terrible?
Well, the report mentions the need for filtering either passive or active filters to actually remove those harmful harmonic currents. And potentially, you might need to increase the size of your transformer and the supply cables to handle the true current load revealed by the PFT.
So it's like this hidden energy waste and damage factor that standard measurements just don't show you.
That's a perfect way to put it, a hidden tax on your system. And it's quite a stark difference, isn't it? It also highlights how even industry standards, like the well-known I-519, they can sometimes give the impression that low-level voltage harmonics and higher-level current total harmonic distortion have a limited effect. Because the standard sets certain acceptable limits.
Which could lead to a false sense of security, I imagine.
It really could be a dangerous illusion, because the reality is power harmonics are known to have a large impact on the electrical system in the plant. They're directly tied to utility penalties in many areas because they distort the grid waveform.
Right, the utility doesn't like getting dirty power back.
Not at all. And internally, they lead to increased energy usage, damage to equipment, and reduced reliability of electrical and electronic systems. And that explicitly includes modern IoT devices, which can be quite sensitive.
So what seems like a small percentage number on paper can actually have these huge ripple effects.
Absolutely. On operations, reliability, your bottom line,
Yeah.
it's significant.
Okay, that's a really solid look at power harmonics and their maybe underestimated impact.
Yeah.
Now let's shift gears. Let's go beyond the main wires and talk about what the report calls the silent saboteurs. Ground and neutral harmonics. This feels less intuitive to me. Why do losses to ground and neutral also count when we're talking harmonic losses?
Yeah, it's less obvious because we tend to think of ground and neutral as just return paths or safety conductors. But electricity is always seeking any path back to its source.
Okay.
And ground and neutral can provide these unintended alternate routes for harmonic currents to flow, especially if the primary paths have higher impedance at those harmonic frequencies. So energy flowing there is still energy drawn from the source, contributing to losses and problems.
Right. So what actually causes voltage, current, and harmonics to show up on the ground and neutral wires in the first place? What's fascinating here, as the report puts it?
Well, there's a whole list of potential causes. It can be induced currents. If you run power cables parallel to ground or neutral conductors for long distances, you can get electromagnetic induction.
Like a transformer effect.
Sort of, yeah. Then you have equipment references. Many devices like VFDs, PLCs, even some single-phase systems intentionally reference their internal electronics to ground or neutral. Unbalanced loads between phases can force current onto the neutral.
Okay, what else?
Simpler things too, like insulator leakage. If insulation breaks down somewhere, current can leak to ground or neutral. Improper connections are a big one, mistakes in wiring the grounding or neutral system. System unbalances we mentioned, capacitive coupling between conductors. And of course, actual fault conditions can dump a lot of harmonic-rich current onto the ground path.
That's quite a list. So the impact of having all this unwanted energy flowing through ground and neutral, it must be pretty significant if they're silent saboteurs. How does it actually affect things in the plant?
It has a really negative effect, mainly because ground is, or should be, a stable 0-volt reference point for so many systems.
Right. Everything relies on that reference.
Exactly. So when you have high levels of ground or neutral energy and voltage and current, it can seriously mess with things that use that reference, like protective relays, making them trip falsely or fail to trip when they should. PLCs can get confused data. VFDs can malfunction. It directly contributes to bearing currents, which we'll get into. And basically any equipment that's ground referenced can be affected.
And it can even hit the transformer.
Yes, and this is scary. These ground-neutral currents can sometimes saturate the transformer core without being measured or identified by relay protection.
Wow. So the transformer could be massively overloaded and overheating due to currents your protection system doesn't even see?
Precisely. Because those protective relays are typically looking at phase currents, not necessarily ground or neutral currents, unless it's a specific ground fault relay. It's incredibly dangerous.
Okay, this leads us to something you mentioned, bearings. The report says something really startling. Electric motor bearing electrical failures are not just caused by shaft currents, but also ground voltage and current issues. I always thought it was shaft voltage discharging through the bearing.
Yeah.
How does ground voltage do that?
Yeah, it's a common misconception to only think about shaft voltage generated by the motor itself, especially with VFDs. But the report clarifies that having an extraordinary high potential on the ground system, especially when you have fast rise time and harmonics present in ground, what we often call ground noise, it basically has the same damaging effect on the bearing as high shaft voltage.
So the voltage difference isn't necessarily between the shaft and the frame, but between the frame connected to noisy ground and the rotor shaft assembly.
Exactly. Or just transient voltages on the ground finding a path through the bearing. The result is the same, bearing heating and electrical discharge, those little sparks across the oil film. And this leads to rapid overheating of lubricants and that characteristic fluting or pitting damage.
And the real kicker here, again, is that this can also occur in applications where variable frequency drives are not used.
Yes, that's critical. You can have a perfectly standard motor, maybe on a soft starter, or even just across the line, and if your ground system is noisy with harmonics, you can still destroy bearings electrically.
The report gives a specific example, right? A 300 horsepower motor on a soft start.
Yeah, experiencing frequent bearing failures. And when they investigated, the culprit was identified as ground noise during startup. The photos in the report apparently showed classic bearing ball damage and outer race damage, textbook electrical discharge machining, EDM.
Wow. Just underscores you can't assume it's the VFD. You have to look at the whole system, including ground.
You absolutely do.
And we shouldn't gloss over the safety risks here either.
Yeah, definitely not. The report is quite clear that the overall losses associated with ground and current harmonic content, depending on the plant-specific conditions, can result in safety issues up to and including arc flash and fires.
So unstable ground, unexpected current paths. It's not just about equipment failure. It's fundamentally about personnel safety.
Absolutely. It's a critical safety consideration that often gets overlooked when chasing down these mystery failures.
Okay, so we've covered external harmonics, power, ground, neutral. Now let's go inside the motor itself, stator and rotor harmonics. Historically, I think rotor heating from harmonics was mostly associated with VFDs, right? And those power system fifth and seventh harmonics we discussed.
That was the traditional view, yes.
But the report says now, with higher ground and power harmonics present in the system, such conditions are not unusual even without VFDs. How does that internal overheating show up?
Well, the report gives a really vivid example. They describe seeing a motor rotor that had discolored slightly, turned a bit blue.
Blue. That means extreme heat, right?
Exactly. It takes a temperature approaching 430 degrees Celsius, that's around 800 Fahrenheit, to actually blue the steel laminations of a rotor.
Whoa. And the kicker?
The kicker was this motor had not operated on a VFD.
So no VFD, but the rotor still got cooked to 800 degrees F. How?
The cause of failure in that instance was ultimately the bearings, due to a combination of that intense heat and electrical fluting damage, likely from those ground currents we just discussed. But the rotor heating itself, that points to internal harmonic currents.
How does that internal heating work without a VFD? What's the mechanism for getting that hot?
It relates to the interaction between harmonic frequencies and the rotor's own operating frequency, specifically the slip frequency. Rotor heating is strongly influenced by the operating slip frequency of the rotor and the fifth harmonic content from the power system.
Okay.
And the report gives this jaw-dropping calculation. For a standard motor operating at, say, 1785 RPM, which means it has a slip frequency relative to the 60 hertz field of about 0.5 hertz.
Right. Very low slip.
Tiny slip frequency. But when you factor in the fifth harmonic, which is at 300 hertz, the math shows that this interaction can lead to something like, wait for it, 14,700 times the normal surface eddy current heating on the rotor bars compared to the fundamental frequency.
14,700 times. Are you serious?
That's the number in the report. It's due to the high-frequency currents being forced onto the rotor surface by that fifth harmonic field interacting with the slip. It's an almost unbelievable amount of concentrated heating energy.
No wonder the rotor turns blue. That's like having thousands of tiny, intense heaters embedded in the rotor surface.
It's a powerful illustration of how even relatively low levels of power system harmonics can have devastating internal effects.
And this ties back to the ground harmonics too, right? The impact isn't just bearings.
Absolutely. The report reiterates that harmonic content in the ground contributes broadly. Overheating of the grounding conductors themselves, interference with all sorts of electronic equipment, VFDs, PLCs, servos, lighting, IoT devices.
Increased shock risk too.
Yes, increased risk of electrical shock because metal surfaces that should be at ground potential might actually have elevated voltages and currents on them. And again, negative impacts on protective relays. It's truly systemic.
This also seems to connect to the motor's actual physical design or even how it's repaired. The report mentions slot and rotor harmonics due to design.
Right. It's not just external electrical factors. The way the stator windings are placed in the slots, the number of rotor bars. These design choices create their own inherent harmonic fields.
And mistakes can happen.
Yes. From misdesigns in original manufacturing right through to improper electric motor repair redesign. A rewind shop, for instance, might change the winding pattern slightly, perhaps unintentionally, and introduce harmful harmonics.
Is there an example of that?
Yeah, the report details a recent field finding on a new design electric motor. This motor had high stator slot harmonics, and the measurable effect was a significant ripple in the motor operating current when it ran.
So the current wasn't smooth.
No, and this ripple represented wasted energy, essentially adding unnecessary load to the motor. In fact, this motor operated more than 5% loaded over another motor in the same application.
Just because of its internal design.
Just because of the winding design creating these slot harmonics.
Yeah.
And the consequences. Lower efficiency, obviously, but also higher rotor temperatures, reduced bearing life, and loading on the motor.
And how did they find this?
Interestingly, it was found during an efficiency claim test. The motor wasn't meeting its promised efficiency, and it turned out to involve a unique winding design that, as the report notes, experienced motor design and repair companies carefully avoid, precisely because it's known to generate these harmful harmonics.
So it's a complex interplay. External power quality, ground integrity, and the motor's own internal characteristics.
Exactly. You have to consider all of it.
Okay, so let's try to connect all these dots now.
Yeah.
We talked power harmonics, ground and neutral, internal motor harmonics. When you put it all together, what's the true ripple effect? How does this whole mess manifest in the real world?
Well, the report says when you combine all these aspects, the combination can have unusual effects. The most common symptom people see is those repetitive mystery failures of bearings and windings. Things just keep breaking, and nobody knows why.
Right.
But it can also spread, affecting other components in the system in unexpected ways. There's a really compelling anecdote in the source material about trying to solve bearing currents. So a common tactic is to use insulated bearings on the motor, maybe on the non-drive-in, and sometimes an insulated coupling or a shaft grounding brush on the drive-in.
Right, trying to interrupt the current path through the bearing.
Exactly. But the report points out that even if you do that, say use insulated bearings and a brush, we can end up with ground noise currents flowing through the coupling to load. The current just finds another path.
So you protect the motor bearing, but now the current goes through the coupling into the pump or the gearbox.
Potentially, yes. And even if you then insulate the coupling to isolate the load, you might still end up with high potential associated with the motor and rotating components because the voltage has nowhere to go. And you might still have smaller levels of current present through the rest of the system, finding sneaky paths.
It's like playing whack-a-mole with electricity. You block one path, it finds another.
That's a very good way to describe it. And this leads us to another critical point. Technicians often don't even look for electrical damage in the driven equipment bearings, the pump, the fan, the gearbox, because, as the report states, common literature points strictly to the electric machine as the source of bearing currents. Everyone focuses on the motor.
But that's the whole story.
Not according to this report. They state they have investigated numerous instances where gearbox, fan, and pump bearings have electrical discharge damage even when isolated from an electric motor, for example, with an insulated coupling.
Wow. So the damaging currents are finding paths around the motor isolation, or maybe originating from ground noise affecting the whole system.
It seems so. It really shows how widespread and insidious this problem can be. It's not just a motor problem. It's potentially a system-wide electrical environment problem.
This has been, well, incredibly insightful, maybe a bit scary too.
Yeah.
So what can actually be done about all this? Are there solutions? We can't just live with failing equipment?
No, absolutely not. And yes, there are solutions. The report briefly touches on a range of approaches. Things like filtering power actively or passively, using harmonic filters to clean up the power supply. Also, specifically filtering ground, using devices designed to reduce high-frequency noise on the grounding system. And crucially, ensuring proper redesigns and inspections of motors, especially when installing new ones or after repairs, to avoid those internal harmonic issues we discussed.
So it requires a multi-pronged approach,
Okay.
looking at power, ground, and the motor itself.
Yeah, it really seems like a holistic approach is needed. You can't just focus on one area.
And just to reiterate, it's not only electric motors that are vulnerable here, right?
That's absolutely right. The report makes sure to mention that, in addition to the electric motor, transformers and other electrical and electronic systems are impacted by high harmonic conditions as well. Transformers can overheat, electronic controls can malfunction, PLCs can glitch. It affects the whole infrastructure.
Okay, so as we wrap up this deep dive, I mean, it seems abundantly clear that electrical harmonics are way more complex, way more pervasive than I think most people realize. They really are this kind of silent, often invisible saboteur that's impacting, well, everything from how long your bearings last to your energy bills to serious safety risks, and even the basic functionality of all our connected IoT devices.
It really is fascinating, isn't it, how these subtle, seemingly invisible electrical disturbances can cause such significant and often baffling physical damage in heavy machinery.
Yeah.
It kind of makes you wonder, if we take this idea, this deep dive approach, and apply it elsewhere, What other invisible or overlooked forces might be at play in other common repetitive failures, maybe in completely different industries?
That's a really provocative thought. Like, how might understanding these really complex interconnected system effects where the problem isn't where you first look, how might that fundamentally change how we diagnose and hopefully prevent problems in the future across all sorts of fields?
Exactly. It pushes us to think beyond the obvious symptom and look for those hidden connections. A really important takeaway, I think.